Welcome everybody to the Machine Learning Needs Mathematical Optimization online seminar series. Today we have the pleasure of having Professor Piccialli, who is a full professor at the Department of Computer Control and Management Engineering at La Sapienza in Rome. Professor Piccialli was prior to this at the University of Rome Tor Vergata, and she was prior to that postdoctoral fellow at the University of Waterloo. Professor Piccialli is a great contributor to the field of mathematical optimization for machine learning, and she has co-authored a very well-known survey on nonlinear optimization for support vector machines. In addition to this field, she works on methodology contributions to mixed integer nonlinear optimization, semi-definite programming, game theory, and applications to chemical engineering and power consumption, among others. Her work has appeared in leading journals in the field, such as Mathematical Programming, European Journal of Operations Research and Transportation Science. She's currently an associate professor in the Info Journal on Computing and Euro Journal on Computational Optimization, and she also has patented some of her work. We are very pleased of having you today here, Veronica. The floor is yours, and as usual, the questions will be taken at the end, but if there is a very urgent question, please put that in the chat, and I will be happy to read it to Veronica. Thank you so much.
Thank you, Dolores. Thank you so much for the invitation. I was saying that I love this seminar series, so I'm really glad to be here. And actually, I'm going to talk to you about the project that has been going on for a while. And everything started when I was still in the University of Rome Tor Vergata, and Angelica Rigele came as a visiting professor for a few months in Italy, just before the COVID started. And we have been working on minimum sum of squares clustering, first in the unconstrained version, and then, which is the main topic of today, in the semi-supervised version. And this is a joint work with all of it with Antonio Sudoso, and part of it with Anna Russo and Angelica Vigele. So, and I will explain you where each one of them comes into play. So, what I'm focusing on is the sum of squares clustering problem. This means that I have n data points in RD, and I want to partition them into k clusters. And I want to partition them in such a way that I minimize the total square distance between each point and the cluster center. So if I have this set of points, and you see here, and I only have k equal to, and I have k equal to 1, then this is what I'm going to get, and my cluster center will be this square point here. If I have k equal to 2, then you see I will get two different clusters in this way, and the square point again will be the cluster center. So, and if I have k equal to 3, I'm always assuming k is even. We'll discuss this later. So then this is what I would get, and by minimizing my objective function. And what is interesting here is that if I have a cluster assignment, then I know how to find the optimal cluster center, and I can find that in a closed form because it's just the average of the points in that cluster. So given the assignment, computing the cluster center is easy, and I can do that in closed form. If I want to formulate this problem, then this is what I get, and as you can see, it's a mixed integer nonlinear programming problem, and where I have my delta ij of the cluster indicator variables, which are binary, and those will be equal to 1 if the point I is assigned to cluster j and 0 otherwise, whereas the vectors and j represent the cluster center and have the same size of the point xi. And again, I'm assuming that k is given here, the number of clusters is given. And this problem is MPR, even if I have only 2 clusters and if I'm considering points in the plane. So even in the simplest form you can think of it, this problem is MPR. And this is a classical problem in the field of unsupervised machine learning, and it has many, many applications. Here I've listed some of them, like image segmentation, credit risk evaluation, biology, document clustering, but there are many, many others. And what is well known is that usually I am applying clustering when I don't have the true labels. So it's a classical topic in unsupervised machine learning. However, if I have some background knowledge on object or some characteristic on the cluster, I would like to include that because the more information I have, the better will be the cluster quality I will get. And I can do that by introducing some user constraints. And mainly the user's constraints can be of two types. They can be instance level constraints. What is an instance level constraint? Well, an instance level constraint can be of two types, either must link or cannot link constraints. Must link means that for some reason, I know that point I and j need to be in the same cluster. I don't know what cluster, but I know that they have to be together. And also, I can have cannot link constraints, meaning that I know for sure that points I and j are not in the same cluster. So these are what are called the instance level constraints, and this can be used to model also some different requirements on the cluster. As it can, for example, if I have some diameter constraints on my cluster, like think about, I know the diameter of each cluster cannot exceed the given upper bound gamma. Well, this implies that whenever I have 2 points that have a distance between them greater or equal than gamma, then I know that they have to be in different clusters. So this implies some cannot link constraints. On the other hand, I could have some split constraints. So I may know that there is some lower bound of the separation between clusters. So that means that points that are in different clusters need to have a distance greater or equal than a certain threshold epsilon. Well, this then implies that whenever I have 2 points that are closer than epsilon, they have to be in the same cluster. So this means that I'm going to have some must-link constraints. Also, another type of background knowledge that might be extremely useful is what is called the cluster level constraint. In this case, I'm having information, for example, on the cardinality of each cluster. So I know either exactly how many points I have in each cluster, or I have some lower and upper bound on the cardinality. So one could think, wow, I have some better information. My problem should become easier. Well, in general, this is not true. The semi-supervised clustering problem is even in practice, and I'm talking about computing difficulties, is harder than the unconstrained one. And here I'm going to try to give you my intuition of it. So assume you have this set of points, you have 300 points, 299 points in the plane, and you know that, actually you don't know, but this is the ground truth. Okay, so this is how you have 2 clusters, and this is the correct classification of these points. However, if you apply the unsupervised classical sum of squares clustering, what you will get is this one. Even if you solve it to global optimality, this is the clustering that you get. And as you can see, it has nothing to do with your ground truth. On the other hand, if you assume you have some partial information, so for example, you have 50 must links, what does this mean? If you see here, you have edges between nodes of the same color. So you know that this couple pair of points have to be in the same cluster. And then you have some other partial information. You have some 50 cannot link constraints. So this time you have edges between points of different colors, meaning that you know for sure that those points won't be in the same cluster. And then you solve the semi-supervised version of the sum of squares clustering, then what you will get is this one. And this is much more close to the ground truth than the unconstrained solution. So you see, on the one hand, adding background knowledge helps so much in retrieving the ground truth. On the other hand, your objective function is leading here. Whereas when you add constraints, you're going completely somewhere else. And this is my personal explanation of why things get a lot harder in practice. So the same thing can hold when I'm talking about cluster level constraints. Look at this example. Here I have my ground truth, and I assume that I don't know anything about the clustering, about the clusters, and I try to solve the unconstrained version. This is what I get, my global optimum. That, as you can see, well, the red cluster is correct, but the other three are not. But if I introduce the cardinality constraint, then this is what I get. So basically, I recover the ground truth. So having background knowledge can be extremely helpful, but in general makes the problem even harder. And we know that it's already hard even without constraints. So what is the state of the art for this problem? Most of the algorithms are heuristic, both for the unconstrained and the semi-supervised version. And in particular, in the unconstrained setting, the most popular heuristic is k-means that we will see later can be used very large scale, and there was a lot of work since it has been defining on finding good initialization for it. If I have only instance level constraints, so meaning that I only have must link and cannot link, the most used heuristic, the most popular one is what is called COP k-means, which is basically a direct extension of k-means, where, however, you may not get a feasible clustering. And then for the cardinality, there are just a few heuristics, and most of them study mainly the case where I'm assuming that all the clusters have the same cardinality, which is the equipartitioned version, and that is, a specific case. And then they try to arrange that solution they found for that case to the different cardinalities, but it's not very studied. And the question that is reasonable is, do we need an exact algorithm? Well, actually, the answer is yes, because clustering results usually require some interpretation from domain experts. And if we produce a solution that is far away from the global minimum, then we might get completely wrong interpretation. So what is the situation about exact algorithms, the state of the art in the literature? Well, one could just try to plug the mixed integer linear programming formulation into solver, but this has been tried somehow. Recently, there have been some different formulation for the cardinality constraint version in this paper of 2021. And also there is a preprint now where some recent ideas for solving the minor field ship have been tried, but still it's a very hard to solve in practice. And for the unconstrained version, this method that we proposed, and I'm going to tell you something about it because I needed to talk about then the semi-supervised. And so we are able to get up to 4,000 points. And before the state of the art was 2,000 points only in the plane, or a larger number was for a very large number of clusters. When you get to the instance level constraints, the situation gets a lot worse in the sense that the state of the art is with repetitive branch and bound that uses constraint programming as the internal solver, but it can only solve instances up to 200 points, so much smaller than the state of the art of the unconstrained case. And also in the cardinality case, in principle, one could adapt any instance level method, level constraint method, but actually there is one that has been tailored that works better for the cardinality constraints, but even there, it cannot solve instances larger than 200 nodes. So let's talk about the formulation, and we start from the unconstrained one because I'm going to need to tell you some ingredients we have used in the unconstrained case to tell you how we changed them, we adapt to the things in the semi-supervised setting. So here is the formulation I gave you before, and actually it can be proved that this is completely equivalent to the nonlinear SDC problem that you see on the right. And as you can see here, your variable is the matrix Z, the square matrix Z, and you have this nonlinear constraint that Z squared is equal to Z. And this is why this is also called the 0-1 SDC problem, because we have an integer problem. And these two problems are completely equivalent, so this is exactly a reformulation of the one on the left. And you can see here that any feasible Z is a block diagonal matrix with a very special structure that can be exploited. So if you have a Z, which is a feasible solution for this problem, then you will have that if you have 2 points I and J that are in the same cluster C, then the rows I and J of the matrix Z will be equal. So the two rows will be identical, and not only the non-zero entries of each rows I and J will be be equal to 1 over the cardinality of the cluster the 2 points belong to. Whereas, if the points I and j are not in the same cluster, then you will have that zij will be equal to 0. To give you an example, if we have 6 points in 3 clusters, so you have one single cluster made by x1, a cluster made by x2 and x3, and a cluster made by x4, x5, and x6, the corresponding z will have this structure. So as you can see, there is a lot of structure in that we will exploit. Okay, so the first part I'm going to talk to you about has already been presented by Antonio in the Young seminar, so I'm just going to recall the basic ingredients that I'm going to need for the semi-supervised version. And in particular, what we have done is to define a branch and bound approach for solving the unconstrained version of the minimum sum of squares clustering problem using these ingredients. We have an LTP relaxation for computing the lower bound at each node, and we solve this relaxation by using a casting plane algorithm. So we strengthen the bound, and this was really the key of success here. And then we have a very efficient primary heuristic that computes an upper bound, and that heavily relies again on the solution of the LTP relaxation. And finally, we have a branching rule that is related to the clustering problem. So I told you that we can rewrite the problem in this way. Well, actually, this can be rewritten in this other way. So again, it's a rewriting, so the problem is still equivalent, but I'm removing the nonlinear constraint z squared equal to z, and I'm imposing that the rank of z has to be equal to k, and z has to be positive semi-definite. Well, in this way, by dropping the non-convex constraint that the rank of z is equal to k, we obtain the classical relaxation as the relaxation that is called by the Penguin relaxation that was introduced in 2007. That is our basic ingredient. Okay, this is our basic relaxation. But then we don't keep this relaxation. We add some varied inequalities of different classes with a casting plane procedure in order to strengthen the bound. How do we branch? Well, at each node, we choose a pair of points I and j, and then we generate two children, because we have two possibilities. Either points I and j are in different clusters, and in this case, we simply add the constraint zij equal to 0 to the LTP problem, or points I and j have to be in the same cluster, and in this case, we will add the constraint that the two rows I and j have to be equal. Actually, we can also shrink the size of the matrix of one element. So we can solve an LTP of size -1. So the question is, how do we choose the branching pair? Well, we use this rule because we know that in a clustering matrix, we need to have either zij equal to 0, and in that case, the points are not in the same cluster, or the two rows I and j need to be equal. So we choose that pair where both conditions are violated sufficiently, because in this way we are sure that both children will benefit from having the constraints coming from the branching, and the bound hopefully will go up. So note that already here in the unconstrained version, we are adding instance level constraints, because on one side we are adding a must-link constraint, on the other side we are adding a cannot-link constraint. So you can see already here that the idea of going to the semi-supervised with instance level constraints made a lot of sense from the beginning. So, but as you know also, for a branch and bound, a main ingredient is the heuristic, because you need to compute also an upper bound, not only a lower bound. And as I told you, the most popular heuristic, which will be the basis of many of the things I'm going to say today, is the k-means heuristic. And the k-means heuristic basically alternates two phases. I have an initialization of centers, which is this one, and then what I do, given my centers, my current centers, I do the optimal assignments of my points to the clusters given the current centers. And this can be done in closed form, because basically what am I doing here? I'm saying, okay, I'm assigning my points to the closest center, so that at the beginning here, the points will be all blue. But then I recompute the centers given the points in the clusters, and this is again done in closed form, so it's extremely efficient. I'm just taking the mean of my points in the cluster, and here is what I get at the first iteration. And then I keep iterating, you see, the two phases. So You see the centers keep moving, the assignments keep changing. And in the end, what is going to happen that at some point, the assignment won't change anymore. And so the centers won't move anymore. And so the algorithm stops when the solution does not change. And I can prove that you always get convergence. But what are you converging to? You're converging to some suboptimal solution, which is the local minimum of our original problem. And the quality of my local minimum will heavily depend on the choice of the centers. And not only at each node, we need the heuristic, not only at the root node, we need the heuristic also in the branch and bound tree. And in the branch and bound tree, we will have some instance level constraints. So we cannot use k-means as a heuristic. We need something that is able to handle some instance level constraints. And this is why we use what is called the COP k-means. In our first branch and bound, we were using just COP k-means because that was enough. We only had a few instance level constraints. And as you can see, COP k-means is basically exactly k-means because I'm alternating the assignment to the cluster to the center choice. But here, when I'm doing the assignment, I'm trying to force feasibility of the constraint. But since it's a greedy assignment, it may happen that the algorithm fails and doesn't give me back a feasible clustering because it is not able to satisfy my constraint. This never happens when you just have a few instance level constraints, but it may happen when you have many instance level constraints. But exactly as if you look at the algorithm here, you see that you're taking in input some initial cluster samples. So exactly like the basic version of k-means, the quality of the clustering you produce will depend heavily on the quality of the initialization. And this is why, in general, there are some standard initialization like k-means plus, which is the most famous, or you can do some multi-start with different center choices, and that will improve the quality of your local minimum. But our idea was this one. I have the solution of my SDP. And if by chance that solution represents a feasible clustering, so it's feasible for the original 0, 1 SDP, then if I compute this matrix M, that is simply the product of my matrix Z times the matrix containing all the points, then, well, I would get exactly k repeated rows, and each of them would be the center of the cluster. Okay, then, if the relaxation were tight, then I could multiply, I could still compute M, and I would get something close to the ideal center. So my idea is I want to build an initialization procedure that keeps into account the solution of the SDP. And basically what I do is to solve the relaxed SDP and obtain my solution. I find the rank K approximation of this matrix, and I use this as an approximation of my Z feasible. So then I compute my matrix M, but what happens here is that I will not have exactly K rows all equal. But what I can do is I can cluster the rows of the matrix M, and this will give me my centers that I will give to COP k-means as initialization. So what I do here, I run COP k-means only once in my branch and bound tree, starting from this initialization of the centers. And just to give you an idea of what happens here, I have 4 different solutions of SDP that I've used for doing my procedure. And every time I go from one solution to another by adding inequalities, so I'm improving the quality of my lower bound. And as you can see, when I cluster the rows, I get closer and closer to the real cluster centers. And in the last one, I get, in this case, the optimal solution. So that is basically the idea. But even in the first slide, in the first solution, you see that I get a pretty good approximation of the good centroid. Okay, so I'm not going to talk about the unconstrained case longer than this. I just want to mention the results. So we were the first one to solve real-world instances up to 4,000 points, and for any that we are not sensible to the size, to the number of features. So that doesn't influence the performance of our algorithm. And what was really the main ingredient was the bounding procedure with the cutting plane, because that allowed us to keep the number of branch and bound nodes really, really low. However, of course, the single node can be expensive. What was surprising, at least to me, is that on 45% or 44% of the instances, we verified the global optimality of some clustering that K-means could not find the root. So K-means is a very good heuristic, but in many cases it does not produce the global minimum. And of course, the real bottleneck is the SCP solver, because when the large values of n and large number of inequalities, the bounding procedure can be extremely slow. And here is the code. So the question was after this, how can we exploit and extend the results to go to the semi-supervised setting? And so what I can do, again, I can start from the formulation of the semi-supervised minimum sum of squares, where, as you can see in red here, I have the mask link constraints, where I'm saying that the pairs I and j have to be in the same cluster. And then I have these cannot link constraints, where I'm saying that the points I and j cannot be in the same cluster. And first, I can add the equivalent constraints on the SDP reformulation, and this will be a reformulation again. And of course, the problem is still NP-hard, and actually determining the feasibility for even only finding the feasibility of general set of constraints is NP-complete. So that some approaches actually do not impose the constraints, but impose some soft constraints or change the distance measure in such a way to keep the constraints into account. What we want to do, though, is to enforce the constraints in a hard way. So we are forcing all the constraints to be satisfied. And what I'm talking to you now is in this archive preprint, and what we have done is to define, so this is the joint work we've done, Russo also, and we define a branch and bound method for solving a problem. And again, we use an FTP relaxation strengthened with cuts to compute the bound. And here, another, like I think one of the main contributions here is the definition of a very efficient heuristic that recalls K-means that can also be used on very large size instances, even larger than the ones we solve exactly. And we managed to solve for the first time instances up to 800 points with a large number of constraints. So it's about 4 times the size of the problems that were solved up to now exactly. So one could say, well, but that didn't change too much. You had pairwise constraints already in the branch and bound tree. So what's the difference? Well, no, there's a lot of difference. It's not a trivial extension, because before I had just a very small number of pairwise constraints, because in my branch and bound tree, I had at most 10, 12 nodes, so I didn't have many constraints. Now I have many of them starting from the roots. And well, there is, however, some good news. Because if I have mask link constraints, I can reduce the size of the problem. And this idea was already quite known in the literature, even though the way for reducing the size was different. But basically what you can do, if you have the mask link graph, like in this example, you compute the transitive closure of the graph, and then you simply replace each connected component with a super point that represents all the points that are in the connected component. So the size of the problem drops because you will end up with a data set where you only have the super points. And so the good news is that the size of the problem decreases. And careful that if you have the special case with only 2 clusters, also the cannot link constraints will induce some mask link constraints. Because you know when you have k equals 2, that if you're not in with 1 point, then you have to be the other cluster. And so this combining the cannot link constraints, you will end up in using some mask link constraints. So you will again reduce the size. As soon as k goes to 3, then you cannot do that anymore. Okay, so what's the problem we solve? Well, assume we have a number f of connected components, and each one is represented by some super points, and you have some matrix T that encodes the data points that have been merged, because of course you have to keep track of what you have merged together. And then you're going to solve, like this problem here will be our SDP relaxation that we're going to solve at each node. And as you can see here, you have a structure that is very similar to the SDP we had before, but now the size is equal to the number of connected components. And you only have the explicit constraints of the cannot link constraints. And of course, you will have a cannot link constraint between points belonging to two different connected components whenever you had a cannot link between points belonging to those components. And also in the objective, you will have to shrink the matrix W having the data points as rows, and you can do that by using the matrix key that was used for encoding the connected components. And basically, your super points will be nothing else than the sum of the points in the cluster I. So you see the structure is very similar to the one that we had before, but we have the extra cannot link constraints and the size is smaller. Again, also in this case, it is possible to strengthen this bound by adding valid inequalities. And in particular, we consider three classes of inequalities that are pair inequalities, triangle inequalities, and clique inequalities. And so they all rely on the structure of the matrix Z, and we separate them and we search for violated inequalities, and we keep iterating our cutting plane procedure until the bound improves significantly. And every time we recompute the bound, we also recompute the upper bound and try to improve the upper bound. And so what is interesting also is that at each iteration, we remove the inequalities we have added that are not active. And in this way, we manage to keep the size of the STP reasonable. So the number of inequalities that we add at each cutting plane iteration doesn't increase too much, and the solver is able to solve it quite efficiently. Okay, so a significant difference with respect to the unconstrained case is that here it may happen that a problem in a given branch and bound tree is infeasible because I keep adding many constraints, and it may happen that I get infeasibility. And as we did in the unconstrained setting, what we are using for solving our SDP is a first order method. So we cannot rely on the solver to detect infeasibility, because what will happen if we have an infeasible problem is that the iterates of our first order method will start to diverge, and I will waste a lot of time trying to understand that my problem is infeasible, and I cannot get an infeasibility certificate. So what we do at each node, we solve the integer feasibility problem, which takes basically 0 time with Gurobi. And so at each node, if this is infeasible, we can simply prune the node. And the other issue that arises from using the first order method for solving the SDT is the accuracy. Everybody knows that they are more efficient in solving large scale problems, but we cannot expect the precision that we might require through inferior point method. So we can only hope for medium accuracy, but since we are using this relaxation in a branch and bound, every time we need to be sure that we get a safe bound on our objective. So what we are doing, we are building an underestimator of the objective function of the dual SDP, and use it as a lower bound than the original problem. In this way, we are always sure that we get a valid lower bound that can be used in the branch and bound algorithm. In some cases, of course, the bound will deteriorate a bit, but we are sure that we do not prune a node that shouldn't be pruned. Okay, so what about the heuristic? Well, in the unconstrained setting, the heuristic was important, but not so important. I mean, after a few nodes, we always found the global minimum. Here, when the number of constraints increases, having a good upper bound becomes crucial. That can really make a difference. And so what is out there in the literature is K-means, which is the one that we used in the unconstrained setting. However, when we have a large number of constraints, it may happen that it fails. And so we end up with nothing. We don't have an upper bound for that node. There's also another heuristic that has been proposed recently in 2020, and here the idea is another one. It's okay, I'm going to solve as usual my unconstrained version, and then I'm going to solve an integer problem for finding a feasible clustering that is as close as possible to the assignment matrix that I found in the unconstrained setting. The good news is that in this case, I never fail, unless the problem is really infeasible. So in this case, the heuristic never fails, So I always get a feasible clustering. However, I'm trying to get a clustering that is close to the unconstrained one, but the unconstrained one might be far away from the solution of the semi-supervised version. So in some cases, the heuristic might produce a suboptimal solution. However, this heuristic works better than copy. So our idea was somehow to replicate k-means, but this time we want k-means. What it's doing is just iterating optimal assignment, optimal cluster computation. So the good news in the unconstrained case is that both things were extremely easy and could be computed in closed form. Now what we are doing is, okay, well, the assignment step is not that easy anymore, but I can still compute the optimal assignment, and I can do that by solving an integer programming problem. So what I'm doing here, I'm taking in input my initialization of the cluster centers, exactly like this. I have my constraints, and then what I do is I say, okay, I compute the optimal cluster assignment, saying solving an integer problem, linear integer problem. And this is solved in basically no time here by Robbie. And given my centers mj, my objective function is simply a constant function. Sorry, a linear function. So this term is constant. So this is really a linear function, and I can solve this very efficiently. And then I compute the centers exactly the way I was computing them in the original k-means. So I take the mean of the data points assigned to each cluster. And I keep iterating until I get convergence, and then I return the clustering. And how do we initialize the cluster centers? Well, remember, like in the unconstrained case, we have the SCP solution. So we can derive a very good initialization of the clusters simply by reapplying the same procedure we did before to the solution of the lower bound problem. Okay? So in the end, our main ingredients are the lower bound, where we solve our reduced SDP problem and add violated constraints until the bound is proved. And here we have less cut in plane iterations than the unconstrained case. So we fail at some point in finding violated inequalities. So in general, in the semi-supervised case, the number of nodes is higher than what we had in the unconstrained case. As for the branching, we do exactly what we did in the unconstrained case. So we select the pair that is more far away from being either a cannot link or a must link, so that we hope to have an improvement in both children. So we have a binary branching again. And we use our heuristic at each node. Not only at each node, but every time we solve an SDP and we get a new solution of the SDP, so a new SDP initialization, we recompute our upper bound. And this really made the difference. So here, the role of the heuristic is much more important than what it was in the unconstrained case. Okay, so here are some just details. It's implemented in C++. We use SDP null plus for computing the bound, and SDP null plus is implemented in MATLAB. These are the characteristics of the machine where we run our instances, so not so powerful, but not so bad. And the algorithm can be efficiently executed in a multi-threaded environment. And again, we have instances encoded with links, so everything is reproducible. So also the instances are there. So because the next question is, how did we generate the instances? What is done usually in the semi-supervised literature is to take some classification problems. So these are all data sets, real data sets, and they're all classification data sets. It can be downloaded either at the UCI or UCR website. And here you see the characteristics. So the number of points ranges between 150 and 800. And the number of features can vary significantly. The number of clusters is given and is equal to the number of classes in the ground truth. And so for each of these data sets, we generate several instances. And what is the difference between one instance and the other is the type and amount of user constraints we are introducing. In particular, what we do is if we have a data set with n entities, then we build sets of constraints that can be either n divided by 2 or n divided by 4 constraints. And we can have either all must-link constraints or all cannot link constraints, or half must-link constraints and half cannot link constraints. How do we generate the constraints? Well, they are all enforced according to the dataset through class partitioning. So for deciding whether 2 points have to be in the same class or in different classes, we look at the ground truth, so at the real level. And for each of these configurations, we generate 5 random set of constraints. So we change seed 5 times so that we have, some significant statistics. And in this, we actually follow the literature of the semi-supervised clustering community. So we do the same instance generation that is done in the literature. So in the end, we end up with more than 300 instances in the end. And I'm going to show you some results. I don't want you to look at the tables because I understand that that doesn't really help. But one thing I want you to focus on, here on each line, you have the average on the 5 instances for the 5 different fields. Here is the name of the data set, the number of constraints we are adding. In this case, you see we are only adding must-link constraints. And since we are adding must-link constraints, the real size of the problem is different from the one you have here, because remember, when I have must-link constraints, I'm reducing the size of the problem. So these are the easiest instances because I'm reducing the size. And what is amazing is how small the root gap is. And the number of nodes here with must-link is still very small, and the times are extremely reasonable, and we have a success rate of 100%. So we solve all of these instances within we put a limit of 200 nodes. So if we get to 200 nodes, we declare failure. And here is what happens, which is a bit worse, when we add only cannot link. So cannot link are less informative and harder to solve. Still, the root gap is still very small, but you see that the number of nodes increases, and we have a few failures. So I think it's 4 or 5 instances. I will tell you that later. And I have it in the next slide, so I will tell you. So in this case, I'm only adding cannot link constraints. So in this case, the size only reduces when I have k equal to 2. Otherwise, it has no reduction. And if I have both types of constraints, this is what happens here. And again, you see the number of nodes increases. The gap is, in some instances, is slightly larger, but still very, very good. And we have a few failures in this case for us and for this data set. Okay. So what about the competitors? So the state of the art in this context was CPR-BBA, which is the repetitive branch and bound where the solver is based on constraint programming. So we run the competitor imposing 1 hour as time limit, and we run our method imposing again either 1 hour limit or 200 nodes. So our method fails either because it reaches 1 hour or because it reaches 200 nodes even before the 1 hour. And here we report, you see the percentage of success. And we could only use the 4 smallest data sets because the method fails as a 0% success rate on larger instances, which was expected because already in the paper they said they could not solve instances with more than 200 nodes. And the bad news here was that if you run the competitor won't give you a feasible clustering until it terminates, because it has an incremental building of the feasible clustering. So you end up after 1 hour with nothing. And so what you can see is that our method greatly outperforms the competitor, especially when cannot link constraints are involved, which are more difficult. And even in those cases where that are met for us as a failure, our branch and bound is usually able to provide a very good clustering solution. So we still give back a feasible solution, whereas they do not, because as I told you, the solution is built incrementally. So we definitely win them. So summarizing, when we only have must-link constraints, we can solve for optimality everything in less than half an hour and with a few nodes. And of course, if I have a larger number of must-link constraints, the size reduces more and I'm even more efficient. When there are only cannot link, the computational time tends to grow larger apart from k equals 2. And we have 4 out of 120 instances that cannot be solved. And the relative gap, though, is still smaller than 0.03%. And when I have both, I only have 2 failures out of 120 instances, but we still get a relative gap not greater than 0.04. So we are able to solve instances up to 800 points, and our method is not influenced by the number of features. But one thing I would like you to focus on is that actually our gap at the root is impressive. And our gap at the root is impressive because our heuristic is working very, very, very well. So we looked also at the performance of our heuristic on its own. And I thought, okay, well, if I do the SDP initialization, I'm requiring to solve an SDP that can be large. So the computational time can increase. What happens if I take my heuristic and for initializing the sample use the standard K-means plus that is used, and that takes basically 0 time? And then I compare with the other 2 heuristics I have in the literature, the one with post-processing and the K-means. And I can what I'm putting here is the percentage of times that heuristic is better than the other in the column best. And as you can see, basically our heuristic initialized with the SDP is always the best. And on this column, I'm reporting how many times I'm getting the global minimum. And well, this is not always, but still, by far our heuristic is the best among the 3. And also here, I'm plotting the gap. These are the box plots of the percentage gap of each on each data set of the 3 heuristics. So I'm not putting the top means that, as you can see, it's never the best here, and it's also some percentage of failures. But as you see here, like our heuristic has always a gap that is much lower than the others from the optimal solution. And even with the standard initialization that can be used also for large-scale data sets, it's still much better than the other competitors. So summarizing, is almost our heuristic is almost unbeaten, and of course it doesn't scale too well if you want to solve the SDP, but you can still use the initialization with K-means plus in order to get a fast heuristic for solving even very large-scale solution clustering, semi-supervised clustering problem, and so it will only take a few seconds to get a competitive clustering solution. Okay, what I told you up to now, and then I'm done, is always on the optimization point of view. What about the machine learning point of view? So one reasonable question is, I'm pretty sure I convinced you that I get the optimum from the objective function point of view. But what about the original problem, the real application? So there are some indices defined in machine learning that are used to decide whether the clustering is coherent or not with the ground truth. And one of these is the rand index that I'm giving here you the expression. And actually there is the adjusted version of the rand index, so adjusted rand index. And here the idea is that this index goes from -infinity to 1, the higher the better. If it's negative, that means that there's basically you're getting a clustering that has nothing to do with your ground truth. And if you're close to 1, then you're getting a clustering that is very good. Okay? So the question is, what happens to these instances when I add constraints and I decrease the objective function of my optimization problem? Do I get an improvement in the adjusted random index? Because this is interesting for the machine learning community, of course. And okay, I'm gonna give you some tables, but since I'm running out of time, I'm not giving you the details. But here I have the adjusted random index of the unconstrained solution. And here I'm talking about cannot link constraints, and here is what I get when I get the global minimum of the semi-supervised version, and here is when I apply the heuristic of the post-processing to the same instance. And here when I have n divided by 4 cannot link constraints, and here when I have n divided by 2 cannot link constraints. And what happens here, and I have a similar table also for the must link and for the must link and cannot link. So what may happen basically are 3 situations. You may have a rand index, adjusted rand index that is basically terrible for your unconstrained version, and you will get an improvement here And your improvement will always be higher when you get the global minimum than what you get just the feasible clustering, but might still be terrible, because that this simply might not be the way to cluster those points. But there are also some cases where you start with the low adjusted rand index, but then your rand index increases significantly. And as you can see, it always increases more when you solve your problem to the global optimality. So what happens, what is the conclusion here, is that if you have background knowledge, you always improve the adjusted rand index, and that if you get a decrease in your objective function, again, you always improve the adjusted rand index. So finding the global minimum can make a difference also from the machine learning point of view. If you use masking constraints, those are much more informative. Sometimes the adjusted rand index is still really, really bad. And in this case, probably the solution is either changing clustering techniques, so you want to change objective function, or you want to apply some kernel to the original data in such a way that your objective becomes more related to your distribution of data. Okay, so last minute, just to tell you, 1 minute really, to tell you what we are doing for cases where you have cardinality constraints. Okay, well, everything we have said up to now cannot be extended when we have cardinality constraints, because the Penguin SDP formulation can only be extended to the case where you have that the cardinality of all the clusters needs to be the same. Has been introduced recently a mixed integer linear programming formulation for the cardinality constraint problem, and this admits both linear and SDP relaxation and can be tightened by adding RLP constraints. And however, the size of the SDP relaxation is proportional to n squared times k. So when k is large, this scales really badly, and so it can be used, but only up n equal to 200. So what we have done, we have defined a new SDP relaxation, which has a better size. And so we managed to solve larger instances, and we also strengthen again the bounds by adding inequalities. Our relaxation is in theory weaker than the one that has been proposed before, but in practice it works very well. And again, we have defined a new heuristic that is based on rounding of the SDP solution of the new relaxation. And we were able to find feasible clustering, for instance, up to 1,000 points with cardinality constraints, and we got a gap less than 2% on most of the instances. And the branch and bound is on the way, but the archive will come out soon. So here are the final some references that I leave you here that I referred to during the talk. That's it. Thank you for your attention.
Thank you very much for your implementation and your very strong results on this beautiful problem. So we now open the floor for questions from the audience. And as you know, please raise your hand and we will give you rights to the camera and the speaker. Yes, so we have a question from Belen. We will give you.
Hello.
Hello.
Now?
Yes, you can speak now. Yeah.
Let me share the video too. Okay, thank you. Thank you for the talk. It's very interesting. It's very, it's really, very good what you are doing with exact algorithms for clustering. And I wonder, well, in one of the last slides, you mentioned the kernel clustering. And I was also, it came to my mind, like these type of methods that look for an exact solution. Have you thought about applying them for the case where, like what you want to decide is also the distance, like somehow maximizing the adjusted rank index, but instead of just choosing the allocation, also playing
actually using directly the adjusted random index would require knowing, the ground truth, which in principle you don't. So I don't think that can be done. But we thought a bit, actually, I have to admit, about how to include the building of a proper kernel in such a way to keep into account the must link and cannot link constraints, so that somehow you are including your information in the you know, in the distribution you are achieving of the data. And we have been trying a few things, but up to now we didn't go that far. I mean, the exact approach can be extended, so we could handle the kernel means, because basically that the heuristic becomes harder, but you can, you know, rebuild the STP and you can still solve it. But we couldn't still we didn't give up, but we couldn't still find a way that could exploit the distances enough to improve always the you know, the final random adjusted random index. But we are thinking about it. That's an interesting question. However, you always have the feeling that the information you have is not enough. So like you may end up completely somewhere else, and then you're solving something that is not related to the original problem anymore.
Thank you. Yeah, I think that is very interesting, and yeah, it's good that it's challenging. There is like more incentive to work on it, I guess. Thank you.
Yeah.
Thank you very much, Belen, for the question. Do we have other questions from the audience? Yeah, I like it very much, the fact that you go back to the machine learning model and try to talk about the quality of that was very beautiful. Yeah.
Thank you. Yeah, but because it's something that you realize only when you keep working on it, and you see that some instances are simply so hard because that, for example, is the completely wrong model. And so you say, okay, I'm taking the wrong number of clusters. In the unconstrained version, especially if you chose the wrong number of clusters, then the problem becomes a nightmare numerically. But also it doesn't make that much sense, because you're trying to find something that is useless, because that is completely wrong from the original problem point of view. So you need to find, you know, the balance between the optimization curiosity and the real problem, because then they're kind of unrelated sometimes.
Yeah, and this is why I like very much your title, because it's not completely unsupervised, which, yeah, completely unsupervised. I think this is what you are saying, that it makes the problem sometimes very hard. So, yeah.
Yeah.
Is there any other? Sorry, go ahead.
No, I just in this conversation, it's kind of like would be very interesting to see kind of like the relation between how hard is the problem, how I mean in terms of finding a solution, but also like maybe how far the heuristics they get from the optimal, and if there is any relation to, for example, you know, how useful it is in practice for machine learning, like as you said, like problems that are, you know, sometimes difficult and make no sense because the number of clusters is not right, or maybe the distance that you're using is based on a, you know, it's kind of like has many features that are not useful or things like that. And if there's any relation about that, because this would make also the finding the exact very important in machine learning, because it will give you information about how, you know, close this cluster is to some kind of reality, which I think is a very
and also I have to admit that I was surprised on how many times actually K-means even run 1000 points would not find the global minimum, even in that constraint case. So it's true that it's a very good heuristic because it's extremely fast, it's easy and whatever, but sometimes that gives you something that is correct, basically. And if you don't have the exact solution, there's no way for knowing that. At least when you are able to find the lower bound, at least you can give a guess. And that is already somehow, you know, informative. You say, okay, I'm not far away more than 10% from the optimum. It's already something. But otherwise, you feel like you're in the dark. I don't know, something.
Yeah. Okay, so thank you very much for your talk again. It has been a pleasure to have you in this online seminar series. And for the audience, please note that we are taking 2 weeks off relating to the Easter break. And we will be back in the last week of April with a young seminar. with, again, 3 junior speakers that we are looking forward to hear from. Thank you very much, everybody. Bye-bye.
Thank you. Bye. Bye.
Thank you.
Thank you. Nice talk, Veronica.